This is module 2 of chapter 5. This module devoted to the solution of system of linear equations by iteration methods. Many iteration methods are available in literature, but here we shall describe two commonly used iteration methods called Jacobi's iteration method and Gauss-Seidel iteration methods. An iteration method starts with an initial solution or initial guess, and using this initial guess we obtain a first approximate solution of the system of equations. Again, using this first approximate solution we obtain the second approximate solution, and so on. So, in this method we generate a sequence of approximate solution of the system of equations, and the process terminates when this sequence of approximate solution converges to a desired root. Let us consider a system of n linear equations containing n variables a11x1 plus a12x2 plus plus a1n xn equal to b1, and the last equation is an1x1 plus an2x2 plus plus ann xn equal to bn. Now, we define some basic terms which are used in this model. Let xik denotes the kth iterated value or the kth approximate value of the variable xi, and xik, this is the vector of the approximate solution, kth iterated approximate solution, and that one is equal to x1k comma x2k comma xnk transpose, and this is the kth iteration solution of the given system of equation. The sequence xk, k equal to 1, 2, 3 and so on is said to converge to a vector x, that one is equal to x1, x2 xn transpose if for each I xi k, the kth iteration value of the variable xi tends to the corresponding variable xi when k is very large, that means when k tends to infinity. Now, let xi is the solution vector or the exact solution of the given system of linear equations. Then the error epsilon I k, that means the error occurred at the kth iteration for the variable xi is defined by epsilon I k equal to xi I. Xi I is the exact value of the variable xi minus xik. Xik is the kth approximate value of the variable xi. The error occurred in all variables at the kth iteration is denoted by the vector epsilon k, and that one is epsilon 1k comma epsilon 2k comma epsilon k transpose. The difference of the errors ek at the two consecutive iteration is given by the error vector ek equal to kth iteration vector x minus the kth iteration vector x, which is equal to epsilon k minus epsilon k plus 1. Now, we define a very important parameter which is associated to any iteration method, that one called the rate of convergence. The rate of convergence of a system of equation depends on the method which is applied to solve this particular system. That one is defined in the following line. An iteration method is said to be of order p, which is should be greater than or equal to 1 if there exists a positive constant a such that for all k the norm of the error vector at k plus 1 iteration, that means epsilon k plus 1, which is less than or equal to the constant a into norm of the error vector at kth iteration power p. If p equal to 1, then we say that the rate of convergence of the method is linear. If p is 2, then we say that the rate of convergence of the method is quadratic. If it is 3, then the rate of convergence of the method is cubic, and so on. Now, we describe the Jacobi's iteration method to solve a system of equations. So, this is the system of n equations and n variables. For this iteration method, we assume that the coefficient matrix is diagonally dominant. This is the sufficient condition for the convergence of Jacobi's iteration method. That means summation j equal to 1 to n and j not equal to I, absolute value of aij strictly less than absolute value of the diagonal element aii, and this condition should satisfied for all values of I equal to 1 to n, or summation I equal to 1 to n and I not equal to j, absolute value of aij strictly less than absolute value of ajj for all j equal to 1 to n. Now, we rewrite the above system of equation as follows. The variable x1 is taken from the first equation of the system. The variable x2 is written from the second equation of the above system of equations. The last variable xn is taken from the last equation of the system of equations. So, using this iteration scheme, we can determine the values of x1, x2 and xn from this expression. Let x10, x20, xn0 be the initial guess or solution of the system of equations. Generally, we consider 0, 0, 0 vector be the initial guess or initial solution of the system of equations, that is x1 equal to x10, x2 equal to x20, xn equal to x10 be the initial solution of the given system of equations. Now, the initial solution is substituted to the right hand side of the system of equation 8 to get the first approximate root of the system of equations. Let x11, x21 and xn1 be the first approximate root of the system of equation, and these first approximate solution are obtained by the following system of equations. That means x11 is obtained by the formula 1 by a11 into b1 minus a12 x20 minus a13 x30 minus minus a1n xn0. That means the initial guess is substituted for x2, x3 up to xn to get the first approximate value of x1. Similarly, the initial guess of x1, x3 up to xn is substituted to get the values of the first approximate value of x2. Similarly, for other variables. Again, we substitute the first approximate value x11, x21 and xn1 to the right hand side of the system of equation 8 and obtain the second approximate root x12, x22 xn2. In general, if x1k, x2k, xnk be the kth approximate roots, then the k plus 1 approximate roots are given by the following system of equations. The first equation is x1k plus 1 is equal to 1 by a11 into b1 minus a12 x2k minus a13 x3k minus minus a1n xnk. That means the kth iterated value for x2, x3 and xk are used to find the value of kth plus 1 iterated value of x1. Similarly, the kth iterated value of x1, x3 up to xn are used to calculate the kth plus 1 iterated value of the second variable x2. And similarly, the k plus 1 iterated value of xn is obtained from the last equation, and here the k is equal to 0 or 1 or 2 and so on. This process is repeated until all the roots converge to the required number of significant figures. This process of iteration is called Jacobi's iteration or simply the method of iteration. But there is a limitation of this method. Basically, the Jacobi's iteration method is not applicable for all system of linear equations. The sufficient condition for convergence of this method is discussed in next slides. Now, we shall discuss the sufficient condition for convergence of Gauss-Jacobi's iteration method or simply the Jacobi's iteration method. The k plus 1 iterated value of the variable xi obtained by Jacobi's method is given by xi k plus 1 equal to 1 by aii into bi minus summation j equal to 1 to n, j not equal to I, aij xjk, where I equal to 1 to up to n. This is the ith equation of the system of equations. if xi be the exact solution for the variable xi, then from equation 11 we can write xi equal to 1 by aii into bi minus summation j equal to 1 to n j not equal to I aij xi j. That means in 11 we replace xj and xi by xij and xi. Now the difference of these two equations gives the kth plus 1 iterated errors for the ith variables, and that one is xi minus xi k plus 1 equal to minus 1 by aii summation over j equal to 1 to n and j not equal to I aij xij minus xj k. Note that xi minus xi k plus 1 represents the error occurred at the kth plus 1 iteration. So, we write xi minus xi k plus 1 by epsilon I k plus 1, that means this is the error occurred at the kth plus 1 iteration for the variable xi, which is equal to minus 1 by aii summation over j equal to 1 to n j equal to I aij epsilon j k. So, this gives the error expression at the kth plus 1 iteration, and that one depends on the error occurred in the kth iteration. Now, the norm of the error epsilon I k plus 1 less than equal to 1 by absolute value of aii summation over j equal to 1 to n j not equal to I absolute value of a j j into norm of the error occur at kth iteration for the variable xj, that one is epsilon jk, which is less than or equal to 1 by absolute value of aii into summation of j equal to 1 to n j not equal to I of absolute value of aij into the norm of the error vector epsilon k. Now, let m equal to maximum among the all expression 1 by absolute value of aii summation over j equal to 1 to n j not equal to I absolute value of aij. Then the above equation reduces to the norm of the error vector at kth plus 1 iteration less than equal to capital M into norm of the error vector epsilon k. Note that the term epsilon k, norm of the term epsilon k is linear, so the rate of convergence of Gauss-Jacobi's iteration method is linear. Again, the norm of the error vector at kth plus 1 iteration is less than equal to m into norm of the error vector at kth iteration less than equal to m2 or m square into norm of the error vector at k minus 1 iteration less than equal to dot 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 m to the power k plus 1 into norm of the error vector at 0th iteration. That means, we obtain a sequence of the norm of the error vector, and finally, we can write norm of the error vector epsilon k less than equal to m to the power k into norm of the error vector at the 0th iteration. So, this expression actually gives the relation between the error occurred at the kth iteration and the error at the 0th iteration. Now, if m is strictly less than 1, then obviously m to the power k tends to 0 for large k, and consequently the norm of the error vector at kth iteration tends to 0 for large k or when k tends to infinity. Thus, we can conclude that the iteration method converges if m less than 1. Hence, the sufficient condition for convergence of Gauss-Jacobi's iteration method is m less than 1 or summation j equal to 1 to n j not equal to I absolute value of aij strictly less than absolute value of aii for all I. So, this is the sufficient condition for convergence of the method. In other words, the sufficient condition for convergence of Gauss-Jacobi's iteration method is the coefficient matrix must be diagonally dominant. Now, we consider an example to illustrate the Gauss-Jacobi's method. The given set of equation contains 3 variables and 3 equations. So, from this system of equation we see that the coefficient of the variable y and z, sum of the coefficient of the absolute value of the variables y and z is strictly less than the coefficient of the first variable x, and we also seen that the sum of the absolute value of the coefficient of x and z of the second equation is strictly less than 10. This is the coefficient of the variable y, and for the third equation we seen that the sum of the absolute value of the coefficient of x and y is strictly less than the coefficient of the variable z. That means the given system is diagonally dominant, and hence there is a convergent iteration scheme for the given system of equations. Now, we write the Gauss-Jacobi's iteration scheme as x k plus 1, that means the kth plus 1 iterated value of x is given by the equation 1 by 14 into 4 plus 3 yk minus 5 zk, yk plus 1 equal to 1 by 10 into 12 minus 3xk plus 2 zk, and zk plus 1 equal to 1 by 20, 16 minus 5 xk minus 2 yk. This is the iteration scheme for the Gauss-Jacobi's iteration, and for this problem we assume that the initial solution be 0 0 0. The successive iterations are shown in the following table. Left hand side represents the iteration scheme, and right hand table gives the iteration values or approximate values at first iteration, second iteration up to 11th iteration. Note that the 10th iteration and 11th iteration, that means the last two rows are almost same. So, we can conclude that the iteration scheme converges to a desired solution, and the solution of the system of equation is x equal to 0.3345, y equal to 1.2186, and z equal to 0.5945, and it is correct up to 4 decimal places. So, this is the final solution of the given system of equation obtained by Gauss-Jacobi's iteration method, correct up to 4 decimal places. We have described the Gauss-Jacobi's iteration method to solve a system of linear equations, and we have shown that the rate of convergence of this method is linear, and in this method the kth iterated values of the variable are used to find the kth plus 1 iterated values of the variables. But if we use the most recent values of the variables to calculate the values of the variable in the next iteration, then a faster convergence scheme can be derived. So, there is a method to find the solution of a system of equations which use the recent values of the variables, and this method is known as Gauss-Seidel iteration method. And now we describe Gauss-Seidel iteration method in the next slides. Like Jacobi's method, the equations are written in the following form: x1 equal to 1 by a11 into b1 minus a12 x2 minus a13 x3 minus dot 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 minus a1n xn, and finally xn equal to 1 by ann into bn minus an1 x1 minus an2 x2 minus dot 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 minus an n minus 1 x n minus 1. Let x2 0, x3 0, dot 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 xn 0 be the initial solution for the variables x2, x3 up to xn respectively, and substituting these values to the first equation of the above system and obtain the first approximate value of x1, and this approximate value is denoted by x11. Next, we substitute the value of x1 for x1, x3 0, x4 0 up to xn 0 for the variables x3, x4 up to xn respectively to the second equation to get the first approximate value of the variable x2, and it is denoted by x21. Then we substitute x11, x21 up to xi minus 1, xi plus 1 0 up to xn 0 for the variable x1, x2 up to xi minus 1, xi plus 1 up to xn respectively to the ith equation of the above system of equations, and obtain the first approximate value of xi and let it be xi1. So, continue this process for all equations and we obtain the first approximate solution for the given system of equations. If xik be the kth approximate value of the variable xi, then the k plus 1 approximate value of the variables x1, x2 up to xn are given by the following system of equations, and the first equation of the system is this one. That one is x1 k plus 1 equal to 1 by a11 into b1 minus a12 x2k minus a13 x3k minus dot 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 minus a1n x1k. That means the kth iterated value of the variables x2, x3 up to xn are used to calculate the value of x1 at the k plus 1 stage. Next, we calculate the kth plus 1 iterated value of x2 using this formula. In this formula, we have used the k plus 1 iterated value of the variable x1, that one is obtained in the first equation, and the kth iterated value of the variable x3 to xn. Using this value, we calculate the k plus 1 iterated value of x2. And for the ith equation, for the ith variable xi k plus 1 is obtained by this equation. Note that the k plus 1 iterated value of the variables x1 to xi minus 1 are used, while the kth iterated value of the variables xi plus 1 to xn are used to calculate the k plus 1 iterated value of the variable xi. And for the last equation, we use the k plus 1 iterated value of the variables x1, x2 up to xn minus 1 to get the value of xn at the kth plus 1 iteration. And this iteration scheme is valid for all k equal to 0, 1, 2 and so on. In compact form, the above equations can be written as the k plus 1 iterated value of the variable xi equal to 1 by a11 into bi minus summation j equal to 1 to I minus 1 aij xi k plus 1, that means the kth plus 1 iterated value are used in this term, minus summation j equal to I plus 1 to n aij xjk. In second term, we have used the kth iterated value of the variables, and this is valid for all I equal to 1 to n and also valid for all k equal to 0 to 1, 2 and so on. This iteration process is repeated until the absolute value of kth plus 1 iterated value of xi minus the kth iterated value of xi, that means the difference between two consecutive iterated values of the variable xi is strictly less than epsilon, where epsilon is a pre-assigned positive number, and this condition must satisfied for all the variables, that means for all I equal to 1, 2 up to n. This number, that means the epsilon, is called the error tolerance of the system of equation. This method is known as Gauss-Seidel iteration method. To illustrate the Gauss-Seidel iteration method, you consider an example. In this system of equations, there are 3 variables and 3 equations, and we have to find a solution correct up to 4 decimal places. In this case, the iteration scheme is this one. The first iteration scheme, that means the value of x at kth plus 1 iteration, can be obtained from the equation or from the expression 1 by 14 into 4 plus 3 yk minus 5 zk. This is calculated or evaluated from the first equation, and from the second equation we get the value of y at the kth plus 1 iteration. This is equal to 1 by 10 into 12 minus 3 x to the xk plus 1 plus 2 zk. And from third equation we obtain the k plus 1 iterated value of z, which is equal to 1 by 20 into 16 minus 5 xk plus 1 minus 2 yk plus 1. Note that in third equation the kth plus 1 iterated value of x and y are used because these two values are already available in from the first two equations. Let y equal to 0 and z equal to 0 be the initial solution of the given system, and all calculations are shown in the following table. Note that the first iterated value of x is 0.28571, and this value is obtained from the first equation by putting y equal to 0 and z equal to 0. The first iterated value of y, that one is 1.11429, is obtained by substituting the value of x equal to 0.28571 and z equal to 0. And similarly, the value of z is 0.61714, and this value is obtained from the third equation of the iteration scheme by putting the values of x equal to 0.28571 and y equal to 1.11429. So, using this concept, we calculate all iterated values of the given system of equations, and note that the last two rows, that means the 6th iteration and 7th iteration values are same. This indicates that the iteration scheme converts to a root, and hence the solution of the given system of equation correct up to 4 decimal places is x equal to 0.3345, y equal to 1.2186 and z equal to 0.5945. Now, we consider another system of equations. This system also contains 3 variables and 3 equations, but this system is not diagonally dominant. We know that the Gauss-Seidel iteration scheme surely converges to a desired root if the coefficient matrix is diagonally dominant, but for this case the system does not satisfy that particular condition. But we consider the following iteration scheme, Gauss-Seidel iteration scheme, to find the values of x, y, z. The first iteration scheme is obtained from first equation, the second iteration scheme for y obtained from second equation, and third equation is obtained from the third equation to calculate the kth plus 1 iteration value of z. Here also we take y equal to 0 and z equal to 0 be the initial values of y and z, and the other approximate values are shown in the following table. See that the 11th iteration and 12th iteration are almost same. That means we can conclude that the iteration scheme converts to a root. That means for this system of equation we obtain a convergent scheme of the solutions, and the solution correct up to 4 decimal places is x equal to 1.0000, y equal to 1.0000 and z equal to 2.0000. Note that the given system is not diagonally dominant, I have mentioned earlier, but for this system of equation Gauss-Seidel iteration method gives a convergent solution. That means the condition, the diagonal dominant condition is sufficient but not necessary for the Gauss-Seidel iteration method. Now, we consider a very interesting problem. Let x1 plus x2 equal to 2 and x1 minus 3x2 equal to 1 be the given system of equation. It can be verified that the given system of equation does not satisfy the sufficient condition for convergence. That means the coefficient matrix is not diagonally dominant. So, for this system of equation we consider 2 iteration scheme. From first equation we obtain the value of x1 for the k plus 1 iteration equal to 2 minus x2k, and from the second equation we obtain the k plus 1 iteration scheme for the variable x2, which is equal to 1 by 3 into minus 1 plus x1 k plus 1 iteration. This iteration scheme is denoted by equation number 7, and we consider another iteration scheme. The value of x1 for the k plus 1 iteration is obtained from the second equation, and which is equal to 1 plus 3x2k, and the value of x2 is taken from the second equation, and that one is x2k plus 1 equal to 2 minus x1 k plus 1. This iteration scheme is denoted by equation number 18. So, for this 2 iteration scheme we obtain the 2 table of values. For the first iteration scheme, that means the iteration scheme for equation 17 is this one. Note that the first iteration scheme, that means iteration scheme 17, converts to a root, and we have seen that the iteration 10 and 11 gives the almost same solution for the variable x1 and x2. That means this iteration scheme converts to a solution, but the second iteration scheme, that means the iteration scheme of equation 18, diverge. Note that the first iteration values and second iteration values and third iteration values and so on, all the iterations, the values of x1 and x2 are gradually increases, and it is very interesting to see that the 10 iterated value of the variable x1 is minus 14,720, whereas in the next iteration, the 11th iteration, this value becomes 44,167, and similarly the 10 iterated value of the variable x2 is 14,722, but in the next iteration this value is goes to or raised to minus 44,165. So, we seen that the second iteration scheme gradually diverges. Now, we describe the convergence cases of Gauss-Seidel iteration scheme by this figure, and in this figure we start the iteration scheme from the point 2 0, and the iteration goes to the second equation x1 minus 3x2 equal to 1, and then it goes to the first equation x1 plus x2 equal to 2, and then it goes to the downward direction to the second equation, and finally it goes to the point of intersection of the equation x1 plus x2 equal to 2 and x1 minus 3x2 equal to 1. The point of intersection gives the exact root of the given system of equation. That means the iteration scheme gradually converges to the point of intersection. Whereas the divergence case of Gauss-Seidel iteration scheme, that means the scheme 18, is shown in this figure. The iteration scheme starts from the point A, whose coordinate is 1 0, and it goes to the first equation at the point B, then it is moved to the second equation to the point C, then it comes to the first equation at the point D, and from D to E and to F. So, see that the iteration scheme gradually diverges and diverges to the infinity. So, this is the diagrammatic representation of Gauss-Seidel iteration scheme when the scheme diverges and does not give any solution of the given system of equations. Now, we compare the direct and iterative methods which are discussed in the first module of this chapter and in this chapter. The direct methods are applicable for almost all types of problems, whereas the iteration methods are applicable only for particular types of problems. In direct method, the rounding errors may become very large, particularly for ill conditioned system, but in iterative method the rounding error is small since it is committed in the last iteration only. Thus, for ill conditioned system of equation, the iteration method gives the better result to give the convergence solution. Direct method gives the solution of a system of equation in one execution, while the iteration method is repeated for many times to get the convergent solution. There is no scope to update the solution obtained in direct method, but it is possible for the iteration method. In iteration method, in each iteration we update the approximate solution to get the more better result. So, there is a scope to update the solution in iteration method. In direct methods, the entire matrix is to be stored into the primary memory, but the iteration methods are applied at a time in a single equation. Therefore, only one equation is to be stored at a time in the primary memory of the computer. So, from this analogy, we can conclude that the iteration method is more better than the direct method, but iteration method is not applicable for all kind of system of equation. So, if the iteration method is applicable for a particular system of equation, then iteration method is more better than the direct method. In this module, we have discussed two iteration methods. One is called Gauss-Jacobi iteration and other is called Gauss-Seidel iteration method. Also, we have shown that these iteration methods are applicable if the system is diagonally dominant, that means the coefficient matrix is diagonally dominant, then these two methods give the convergent solution. Also, we have shown that the rate of convergence of these methods is linear. Also, we have discussed the merit and demerits of direct methods and iterative methods and have concluded that the iteration methods is better than the direct method if the iteration method is applicable for the particular system of equations.